Thank you, Dr. All right, thank you very much. Thank you very much for the invitation to speak. So I want to acknowledge at UTK, my current research group, Sophia Han, Spencer Boulogne, and Xingfu Du. And of course, I want to acknowledge the continuous support of my wife and my daughter in back. But yeah, I want to talk today about this gravitational wave merger, or the gravitational wave signal from a neutron star merger. And so this is the New York Times article from October 16th. And so this was a big thing. And it was the first detection of gravitational waves from a merger of two neutron stars. These neutron stars are 100 million light years away, but the signal, the gravitational wave signal, was finally observed on actually August 17th of I believe August 17th of last year, and then finally announced a couple months later. So basically today, I want to talk about why this is important and how this is connected to UT research, at least some of the connections. So, I have attempted to target this at a level which is interesting and useful. Certainly, please feel free to ask questions. Let me know if I'm going too slow or too fast. I'm happy to explain any of the details that you're curious about. So I'm going to talk just a little bit about why neutron stars are interesting and what they are relative to so-called normal stars. Then I'm going to talk about gravitational waves and LIGO and the actual event and what a neutron star merger is, and then the connection, as Catherine alluded to squishiness, which is my favorite way of describing this particular property of neutron stars, which is most relevant for gravitational waves. So my claim is that neutron stars may help us answer fundamental questions about the universe. And so I want to start with a fundamental question: what are you made of? And so this is an audience participation. Somebody has to answer the question in a biological sense, at least. What are you made of?
A lot of carbon and hydrogen and stuff like that.
Yeah, exactly. So, simple atoms and molecules, and basically I think of, the human body as 70% water. Okay, so just 2 hydrogens and 1 oxygen, and this is what you are made of. Okay, and we know, of course, water is made of hydrogen and oxygen, and in particular matter, these atoms are made of neutrons, protons, and electrons. And this is somebody's cartoon I stole from Wikipedia. It turns out, actually, this cartoon is about as good as it gets. You would be amazed. The nuclear physicists in our department even struggle with getting a very good picture. You can't take a picture of an atom. You can't take a picture of a nucleus. So we're sort of left with cartoons. But in the center, you have the neutrons and protons. We call that the nucleus. And outside, you have the electrons. And so if you, for example, you can go to Wikipedia, and you can look up the neutron. OK. So we look up the neutron, and it has this great big description here, and finally you get down to the mass, okay? And it has 10 to the minus 27 kilograms, which of course is a very small number, and we don't like working with numbers that small, so we have this new unit called MeV. And so we're just going to stick to MeV. You can think of it as kilograms or whatever. It's just a funny label. We call it MeV, and it's about 940 MeV. So that's the mass of a neutron, 940 MeV. And then we ask, well, what is the, we know water is made of hydrogen and oxygen. Oxygen is made of neutrons. Neutrons are made of quarks. Okay, that's great. We've learned something. So 1 up quark and 2 down quarks. Okay, so let's go to the up quark and see what Wikipedia says about the mass of an up quark. Okay, so an up quark, we go down to mass here, and MeV, I'm sorry if this is too small for you in the back, but basically an up quark is 3 MeV. I actually said 3, it's maybe closer to 2, but okay, 2 or 3 MeV. Much, much smaller than the mass of the neutron, right? Well, and if you go to the Wikipedia page, of course, for the down quark, it turns out its mass is 5 MeV. Okay? So a neutron is 940, and up is 3, and a down, and there's 2 downs, and this, so that 13 MeV. Right, and there's no way you can get 940 out of 13 MeV. Okay? So this is sort of a fundamental craziness about how the neutron and proton work. And this fundamental craziness is related to the theory of strong interactions, what we call in nuclear physics quantum chromodynamics. Okay? So where is this missing mass? Well, we have kind of a general picture in nuclear physics. We're refining this picture over many years, but the basic answer, well, it's a combination of confinement plus the spontaneous breakdown of chiral symmetry in QCD. Okay, that's the technical answer. Fine, but what I'm telling you is that exactly how this works, exactly how you get from 13 to 940 is not fully understood. And in particular, neutrons and protons as fundamental objects, understanding their size, their spin, their mass, what happens to them as you put them in nuclei, these things are not yet at all fully understood. And in particular, for example, some of you may have heard about the Higgs boson. The Higgs boson actually doesn't help you at all here. Even though it's advertised as the origin of mass, the Higgs boson is actually responsible for the 13 MeV. It doesn't get you to the 940. Okay? So it's this fundamental thing that in neutrons, up and down quarks inside matter behave as if they were much more massive than they actually are. And this is the sort of fundamental question. And what's the connection to neutron stars? Neutron stars are one of the few places in the universe where it's possible that quarks actually behave. That is, they don't carry around this extra mass. So it may be possible to look at a neutron star and to observe and confirm that there are quarks inside the neutron star that behave as if their mass is really 5 MeV and not that don't carry around that extra 300 MeV for each quark. So the other fundamental question, okay, where do you come from? All right, well, this is a biological answer, okay, mom and dad. But maybe you might think about at a little more microscopic level where your atoms come from. Well, atoms are somewhat transient objects in the sense that electrons are transferred between atoms quite readily. Okay, so static electricity just does this. So your electrons move around quite a bit. However, your nuclei, the neutrons and protons in the center of these atoms, does not change significantly over the course of maybe your entire lifetime, except for a handful of things like potassium in your body, okay? So this is just to say that nuclear reactions are a little bit more rare than chemical reactions. And so for that reason, the nuclei, which are on the Earth and in your body, they were originally created someplace else and then put together to form you at some point. And of course, all that putting together is some process. And so we refer to this, sort of where nuclei are created question in our field as nucleosynthesis. And nucleosynthesis has been part of the field of nuclear physics for about 50 years. And so basically, you can think of sort of 3 different classes of nucleosynthesis: light nuclei, hydrogen, helium, which turns out not to be biologically important, and lithium, and some of lithium created in the Big Bang. And so some of the, of course, some of the protons in your body and deuterons also were created in the Big Bang. And then finally, arranged on the solar system and on Earth and now in your body. The medium mass nuclei, everything between lithium and, say, about iron, okay, were created in main sequence stars. And main sequence is just our funny way of saying normal stars. So you look at the sky, the points of light, they're almost all normal stars. Of course, actually, they're not typically single stars. Many of them are binary stars. But this is the main sequence as you can think of a normal star, as opposed to a neutron star, which is a funny, completely different sort of beast. And then heavy nuclei. And so nuclei heavier than iron are mostly created in 2 different sites. And this sort of heavy nucleosynthesis is what I want to focus on today. So just now that we Yeah. Okay. So just to explain, I want to talk about normal stars before we get into neutron stars. And this is the famous Hertzsprung-Russell diagram, been known for many years. And so this is the so-called main sequence. It has main, but these are just all normal stars. Okay. So you can, for the moment, ignore all the stuff here. White dwarfs are very small and hard to see. So one of the things you notice about this main sequence, about this Hertzsprung-Russell diagram, there's blue up here and red up here. And so these different colors also correspond to different mass. So again, it may be difficult to see in the back, but these are like 30 and 60 times the mass of the sun. The sun is somewhere here in the center. So these are heavier, and these here are lighter than the sun. And so in astronomy, mass determines color, and mass determines luminosity, mass determines lifetime. Okay? High mass stars are blue, low mass stars are red. High mass stars have very large luminosity and a very short lifetime. Low mass stars have a very small luminosity and a very large lifetime. Some of these stars down here live longer than the current age of the universe, while these maybe live only millions of years. Okay? So this is the normal stars, and mass determines lifetime and color, but mass also determines the fate of a star. Okay, so you have protostar. This is, and then and then right here, actually in between the red and sorry. Time goes from the left to the right. Let me just explain it in detail. Time goes from left to right, and mass goes from bottom to top. Okay, so these are high mass stars. Extremely high mass stars, they go straight to black holes. Okay? And so black holes are cool and interesting, but I'm not going to talk about them as much today as I'm going to talk about neutron stars. Low mass stars just skip, and they just sort of end up as brown dwarfs. So sun-like stars, they go through a red giant phase, and my apologies, this text is a little bit small to see, and then they end up as white dwarfs. So somewhere in the middle, between black holes and white dwarfs, you end up with a star which originally has a mass of between 8 and 20 times the mass of the sun. Okay? So these stars are more blue, more luminous, a little bit shorter lifetime than the sun. They go through a type 2 core collapse supernova. And this huge, tremendous explosion, and then you're left with a neutron star. Okay? So these are the main sequence, the normal stars here. And these are sometimes I tell people I do astrophysical gerontology. I study, old stars. So neutron stars, white dwarfs, and black holes. And my favorite are the neutron stars. So that's a very quick introduction to the astronomical zoo. Now I wanted to connect this to the nucleosynthesis, right? So as I mentioned, for the heavy elements, there are 2 sites for heavy element nucleosynthesis. Nomenclature, we call them the S process and the R process for slow and rapid. Excuse me. So the S process actually occurs in late stages of normal stars. And I'm going to switch from the PDF to the YouTube here. Okay, so this is the evolution of a massive star, and it actually turns out it has a companion. It has a black hole or a neutron star companion. And during the very late phases, Stella's really excited about this. During the very late phases, this massive star, it pulses, it moves in and out, and these thermal pulses are accompanied by matter being, sort of flown off in every direction. Okay, and so a lot of this matter that's being flown off, these are heavy nuclei that have been created in the star and thrown out into the interstellar medium, and then eventually form heavy nuclei here on Earth. So this is just a YouTube video of a simulation. Okay, so that's one. So that's the S process. And now the other I mentioned is the R process. Okay, so the R process actually, oops, no, don't do that yet. Getting ahead of me. Okay, that's fine. The R process is a fun history. For basically the past 30 years, everybody thought it happened in core collapse supernova. In particular, there's this article in 2004. It says it must happen in supernova. Everything else is impossible. And about 5 years ago, all the supernova people said, we give up. Sorry, we can't make R process nuclei in supernova. It must happen in neutron star mergers. And so one of the exciting things about the LIGO result from last year is a confirmation of this relatively recent idea that neutron star mergers are the site of heavy element nucleosynthesis, are the majority site for R process nucleosynthesis. And of course, there's a cool movie for this one too, which is done by NASA. Hopefully I muted it, okay. Yeah. So they have this wonderful introduction, and then they show density contours, but these are two neutron stars, okay? And they're slowly merging together, and you see matter is transferred between them. It gets extremely messy. You end up with these funny tidal tails, and at the end, you're left with a black hole, okay? And so this is a video which kind of represents what's happening at a basic level in a neutron star merger, and indeed, in this merger creates nuclear reactions which create heavy nuclei, and these heavy nuclei are distributed out to the interstellar medium through all of this sort of matter, and maybe there are contributions from the disk. Okay, so that is now believed to be the site of heavy element R process nucleosynthesis. Okay. That's right. That's exactly. This is the one we're talking about. And just to sort of summarize along the periodic table, we have Big Bang is the light elements, right? And there are some funny details I didn't talk about. The massive stars, the main sequence stars here are here in green. That sort of S process is dying low mass stars are here in yellow. But the cool ones in my book are the merging neutron stars. This is in orange. Okay, and so you see most of the heavy nuclei are created in R process nucleosynthesis, and the largest contribution from that is likely in neutron star mergers. In particular, iodine here is the heaviest element required for life. Iodine is important for thyroid function, I believe. So that is to say, yeah.
What's the source or sources of energy for creating these heavy elements in these processes?
Yeah, it's the gravitational energy. It's exactly just the binding energy of the neutron star. Yep. Okay, so just to check on status here, some of the nuclei in your body were created in neutron star mergers, and understanding neutron stars may tell us about the missing mass and tell us fundamental questions about how our universe works. So, no. Okay, we'll do it that way. So on August 8th, I guess I'm trying to remember exactly what this date is. Maybe it's not. I think actually it's August 17th, and this 8 was a copy of the month. So my apologies for the typo. The LIGO, which is the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves from two merging neutron stars. And then one of the cool parts about this particular story, which I'll not have the time to talk about today, is that several observatories actually, like Hubble and other astronomical observatories, detected the light, the photons, because gravitational waves, right, they're fundamentally different. They're not photons. They're not radio waves or X-rays. They're a completely different kind of phenomenon.
Where's this observatory?
There's one in Hanford, Washington, one in Livingston, Louisiana, and there's one in Europe. They're currently building one in India and Japan. So, of course, we have to talk about mergers. No, I want desktop one. I think I closed this. It's my fault. So black holes are a little bit, no, this is not useful. Black holes are a little bit more interesting because their GR is a little bit more stronger. So this is a movie of a merger And what you see, these are the black holes, and of course you see all this movement around. All this movement is not actually the black hole, it's the distortion of space and time created by the black holes. And that's what I want to focus on here, is this stretching and squishing, if you like, of space and time. And so you see here at the very end, you see even the stars out on the very edge of this grid are stretched and squished at the end. Oops, I didn't go back far enough. Okay, so you see stretching even out to the very ends here. And what that effectively is, that is a visual representation of the gravitational waves. Okay? So a merger like this, the stretching and squishing of space created by these two black holes merging, creates gravitational waves that emanate outward. And neutron stars do the exact same thing.
What's the natural time reference for those mergers from what you're recording there?
Yeah, so this is a good plot here. Of course, the merger happens slowly over billions of years, right? But the gravitational wave signal is detectable for between maybe 10 and 1,000 seconds. Okay, so gravitational waves can be generated by black holes and neutron stars, which are stretching and squishing space and time.
Are the gravitational waves from neutron mergers intense enough to be detected?
Yes, that is exactly the detection which was there, and I'll talk about again.
Could you repeat the question?
The question was whether or not gravitational waves from neutron stars can be detected. Yeah. So gravitational waves, a simple description, they're exactly traveling modifications in space and time. And so gravitational waves are exotic in the sense that they don't require a medium other than just the vacuum of space. Okay? So if you think of water waves, water is pushing around water molecules, right? Or light is pushing around photons. Gravitational waves don't, they're just pushing around space and time. Okay? So when a gravitational wave passes through your body, depending on how it's aligned, what it does is it alternately stretches you. It makes you, depending if it's aligned with your body, it stretches you, and then it squishes you, and it stretches you, and it squishes you. Okay? And so this is the actual signal. Okay? And you can think of the positive sign as the stretch, and the negative sign as the squish. And so it stretches, squish, and it goes back and forth. Okay? So this is what gravitational waves do. And this is the Laser Interferometer Gravitational Wave Observatory. This is the Hanford one in Washington. And what happens is when the gravitational wave passes by, it stretches and squishes these long arms, and that's measured by some laser, and then it's converted into a signal. So of course, as I mentioned, neutron star mergers can generate gravitational wave signals. Okay? And it's all about squishing and stretching, right? So it turns out that if I have a model of a neutron star and I want to ask, is that neutron star likely to generate gravitational waves? The question is how squishy is it? Because if it's really squishy, it's really good at generating gravitational waves. And the more sophisticated way to say this is just a tidal response. This is just how the neutron star is affected by tides, similar to how the Earth is affected by tides. So the Earth, you can imagine this is the Earth, and the moon is over here. And what do tides do? Tides extend out the water and land on the front and back side, and they push in the water and land on the other side. And so it's very much like a tidal force, like the tides responsible for the moon. Tides caused by the moon, sorry?
So ebb and flow.
Yes. So of course, the tides have been described for many years. This is a long classical physics question. In 1911, Augustus Love investigated the tides. He found there are 3 numbers that are important in describing the tides on the Earth, and these are the so-called love numbers. Okay? So Love, not Love, it just happens to be his name. Okay? And so it turns out that we have renamed this for no good reason. We also call it now tidal deformability. Okay? That is the the response of an object to a tidal deformation or to a tidal force. Okay? And so what we want to know is, are the neutron stars squishy? Do they have a large or small tidal deformability? What is the likelihood that they'll generate a gravitational wave? And so when I arrived in at UT in 2014, January 1st, 2015 about, okay, this is one of the first things that I went to work on. Okay? So, and it turns out that you can sort of change the question a little bit. Instead of measuring squishiness, all you have to do is measure size. Because for neutron stars, radius is correlated with tidal deformability. If a neutron star is very large, it's very squishy, okay, for a fixed mass, right? If you make this, you take the same mass and you make it more compact, it's less squishy. That kind of corresponds with our intuition, and it turns out it works with neutron stars. So all we have to do to predict squishiness and predict gravitational, the wave signal, is to measure neutron star radii. And so I have some expertise in analyzing neutron star radius observations. I'm a theorist. I do a lot of the computational and modeling side, but I collaborate with many excellent observers. And so here's the principal data set. There are 7 globular clusters here, and it turns out there are, so most of these are just normal stars, like main sequence stars, like I discussed earlier, but just a handful of stars in each of these images are neutron stars. And out of that handful of neutron stars in each image, it turns out only about 1 is useful for neutron star radius measurements. Okay? So actually 2 in this one. And so Hubble and Chandra and other observatories spent a lot of time looking at these. M13 is a great one. So 47 Tucanae, Omega Centauri, these are the brightest globular clusters in the sky. Unfortunately, they're in the southern hemisphere, so they're more difficult to see. M13, you can see in the constellation Hercules during the summer in the northern hemisphere. It's relatively easy to pick out. It's right in that central box, and there are a lot of good amateur astronomer photos of M13, and there's 1 neutron star in there. And so through some...
Where is it in that picture?
Yeah. Yeah, good question. I have no clue.
How do you distinguish?
How do you know it's a neutron star?
Yeah, so this is the optical, right? It's much easier in X-rays. Neutron stars are copious emitters of X-rays. And so if you look at this in X-rays, it looks like about 10 points of light. And then you just have to distinguish which are accreting black holes versus neutron stars.
The normal stars are emitting lower energy radiation.
Their peak is more in the optical, so their emission in X-ray is much weaker. Yep, exactly. So, okay, so there's some mathematical machinery which you can read about if you like, but basically I used this data to generate predictions for neutron star radii. They're small. Their radius is less than 13 kilometers. You can think of them as the mass of the sun and the size of Chicago. Okay. Extremely dense objects, very sort of cousins of black holes, but because they have a small radius, they have a small tidal deformability, a small squishiness. And so this is a probability distribution. I've plotted this tidal deformability, lambda. This is this funny logarithmic axis, so this is actually 1 in these units. This is 2, this is 0.9, and back down to 0.4 here. Okay, so, but if I made these predictions in 2015, what does LIGO say? Okay, and so LIGO produced their principal work last year in an article in Physical Review Letters, and this is their plot here. And unfortunately, they chose to use a different lambda than my lambda. So they have an uppercase lambda, which is defined with different units, which is just normal messiness. But basically, my constraint, my predictions were that the tidal deformability, this is 2 neutron stars. Of course, there are 2 neutron stars involved, and they each have their own squishiness because they have different mass. And so my prediction was down here, and sure enough, their results are right down here. Okay? It's difficult to see on this plot, but this is the quote from the paper. That's a 95% upper bound, inferred with a low spin prior. less than 970, that's their result, begins to compete with the upper bound of 1,000, that was my result, from X-ray observations in 168. Okay? This is a very academic way of saying they agree with my result. They would like to do better, but they can't yet. Okay, so it is kind of a competition, but anyway. So that's the prediction on squishiness, and that's how we make predictions about neutron stars and gravitational waves. And on the technical side, I use Bayesian inference, which is a fun story. Bayesian inference is a way of approaching statistics, which is sort of pioneered by this Reverend Thomas Bayes in the, I can't remember, I think late 18th century. Long time ago, and it's a very simple relationship between conditional probabilities and prior distributions. For the statisticians, this sort of technique fell out of favor in the statistics community until maybe sort of World War II-ish, and even the past 20 years. Real huge resurgence in Bayesian statistics. This is an excellent book by a wife of a colleague of mine. And Bayes' theory is the theory that would not die. And this is a great story of how it impacted World War II, for example. And I use Bayesian inference. And of course, what am I doing in the future? I have these excellent postdocs and graduate students, and we're looking at each of these boxes here, and each of these pluses are more neutron stars, different kinds of data. And what I'm trying to do is put together the neutron star radius data, LIGO, and all together in one big sort of complete holistic picture of how neutron stars work. And this has required more exotic physics. It turns out that not only are neutron stars exotic general relativistic objects, they're also macroscopic quantum objects in the sense that their neutrons are superfluid. And you can actually visibly see manifestations of that superfluidity in how they rotate. So just to summarize, I do think that neutron stars have the potential to answer fundamental questions about our universe and to teach us where we came from. Gravitational waves are exciting. They provide a new window into neutron stars and how our universe works. They have the possibility in the future of telling us about cosmology, about how the universe is evolving. So this is this whole new field of, well, relatively new-ish field of what we call multi-messenger astronomy, where we use photons as messengers, but also gravitational waves are new messengers. Of course, our research group's predictions of tidal deformabilities are so far spot on. Okay, and we'll see how that evolves over time, and we continue to try to push the frontier in neutron star data analysis. So thank you very much.
Sir?
Question?
Yeah.
If there's quite a bit of heavy elements scattered around, as evidenced by you and me.
Right.
But mergers of stars, even neutron stars, how common is that they are close enough to merge and continue to merge?
So I mentioned this 2004 paper, and this is exactly the argument of the 2004 paper, that basically neutron star mergers they're so rare and they take so long that they can't possibly explain all the R process material in the solar system. And they are, so getting two neutron stars next to each other and getting them to merge in a finite time, in 13 billion years, is not easy, but it turns out there are more of them than we thought, and enough of them. I couldn't tell you necessarily the number of neutron stars per unit volume in the universe. I don't have that number, but it turns out there are enough of them to. Yes?
What determines the frequency and amplitude of a gravitational wave?
Yeah, good. So the frequency just increases over time, and one proxy is the distance, or is the period, right, of the motion. So as they're far away, their period of the motion is relatively long and the frequency is relatively low. As they spiral in towards each other, the period of the motion decreases, so their frequency increases, until finally it reaches a peak frequency just right about when they merge. And then the frequency dependence is determined by sort of oscillations on the surface of the black hole instead of the period of the motion. So the amplitude is determined by, is similar. It's low. It's small amplitude when they're far away, and the amplitude increases, increases, increases. It reaches some maximum, and then it falls off.
But LIGO detected gravitational waves that traveled through the Earth, correct?
Right.
And once those black holes merged and the waves were emitted and traveling through space toward Earth, was their frequency and amplitude constant, or did things change?
So as they, though the waves, the frequency and the amplitude at the point which they're generated, right, change as a function of time. And as the gravitational waves proceed throughout the universe, those frequency and amplitude are not changed significantly. There's almost no scattering. Basically, unless you happen to pass through another pair of black holes, which is right at the resonant frequency, you don't even see them. So they go right through. This is the cool thing about the gravitational waves. They fly right through the universe, and they barely see anything. And this is also why they're so hard to detect, of course. Yes?
So then what is it about neutron stars that makes them special and able to interact and even generate gravitational
So
waves?
neutron stars, the gravitational wave signal from neutron stars is not quite as strong. But the cool thing about neutron stars is you can actually see them.
The actual star itself.
You can see the star itself, but in principle, the real critical thing over this last detection is you see the X-rays emitted after the merger. So all this detritus that's hanging out near the merger after the event, you can actually see.
But is it their mass that makes them able to interact with, or able to generate the gravitational waves?
It's the principal determining factor in its, its compactness and then also squishiness. Yeah.
LIGO is quite old. I forget when it was first proposed.
Yeah, a long time ago, yeah.
They've gone through upgrades.
Yes.
And it's my understanding they just went through this last upgrade just before this happened. Is that correct?
Yeah, so they have, they're in the middle of a big upgrade, okay? Yeah, and they have runs where they're taking data for a month or something on that time scale in and amongst the upgrade. And so this happened during this upgrade. So they won't be to their full sensitivity until I think sometime in 2020. And in fact, I don't think they're taking any data at all in 2018 because they're upgrading the equipment.
What's the length change they can measure right now?
I don't. The limit on the strain sensitivity is very frequency dependent. It turns out they're great for measuring these frequencies, but as you get to high frequency, you're limited by their electronics, and low frequency seismic noise is a huge problem for them. They have crazy background like clouds. They see clouds moving in the sky above the detector, and it's part of their background. So.
I mean, what's
The length, yeah, it's something like 10 to the minus 23 meters, something.
You're kidding.
Yeah, it's very small.
Like 100th the size of a proton or something like that.
Well, that would be 100,000th of the size of a proton, I think, yeah, or something like that. Other questions?
I have lots of questions. I'm having a really hard time trying to start with basics. One is that are all neutrons, if they stood alone, the same?
Are all neutrons the same? Yeah, we believe so. We don't have any evidence to the contrary yet.
If that's true, what causes them to want to associate with each other to the point that you have a neutron star huge mass,
Yeah.
but nothing to hold it together.
Yeah, so gravity holds them together. So all neutrons are the same. All neutron stars are not quite the same, right? The big difference in neutron stars, just like normal stars, is mass. Mass determines size, fate, luminosity, everything, okay? So
When you talk about squishiness, it has something to do with how far apart the neutrons actually are in the star.
yeah, it does. Yeah, squishiness does depend on the density, and the density tells you how far away any neutron is. That's right. And of course, the reason why the neutron stars aren't next to each other is because they originally started as a binary star system, and then both of those stars evolved through the supernova to create a neutron star. And most stars you see in the night sky are binary stars, so they're actually quite common. Binary stars are quite common. Neutron stars, double neutron stars are not as common, but yeah.
What is the permissible range for mass for a neutron star? And is that such that every time you get a merger of neutron stars, it must become a black hole?
That's an excellent question. We have no idea. No, we have a little idea, but we would like to know more. So we believe there's a lower limit about the mass of the sun. Okay? We have recently, only in the past like 4 years, found neutron stars twice the mass of the sun. And even then, seeing that was a revolution. Like, that was a big deal for us. We believe from theory models like the theoretical models that I construct, the maximum neutron star mass is somewhere between, well, 2, it has to be above 2 since we see some at 2, and maybe 2.7. Okay? So then the question is, how many of these pairs generate neutron star remnants, or do they generate black holes? Like 1.4 plus 1.4, very typical assumption in our field, and more than likely generates a black hole because it's 2.8. But if you have a 1.0 plus a 1.0, we believe that probably generate a neutron star. This is one of the critical questions that LIGO hopes to answer in the coming years. Yeah.
Said there were 3 sites and they're building 2 more.
Yeah.
So they're upgrading them all at the same time.
So the European site, I don't know. I believe they're upgrading it, but I don't know their time schedule as well. The one in India has not yet been. It hasn't even. They don't even have the construction, the basic. I think they haven't started at any level yet. And the one in Japan, I think, is still in the planning stages.
Would neutron stars be more visible if they're resided by something that's outside the solar system?
Well, the closer they are, the easier they are to see, in all cases, right? So this merger we saw out to 130 million light years, right? But if it was closer, we would be able to see them easier, and our signal would be better, the data would be better. So that's actually a far distance. In terms of observations of other neutron stars, not just mergers, there are some neutron stars which are only maybe 100 parsecs away, and so we can see them from Hubble and other X-ray instruments, X-ray observatories. There are some visual pictures of neutron stars, single neutron stars, but they're really boring. They're like points of light. They're just so small. It's not their distance, it's their size. 13 kilometers is really small.
Have you ever thought of Asst writing one of those black and yellow books? It's an idiot's guide to neutron stars.
I haven't yet, but there's no reason that's not. Yeah, there was a question here.
I was wondering, do you think it's possible to predict like how possible it would be for gravitational waves to like combine the way that we see other waves combine?
Yeah, so gravitational waves you can add them together. They obey a superposition principle just like electromagnetic waves. Unfortunately, they're relatively rare, and so the place where superposition is likely to be an important effect is gravitational waves generated in the Big Bang. in the early part of the universe. And so these sort of relic gravitational waves, you might be able to see, and superposition might be important there. That's what comes to mind.
What did Einstein predict relative to the gravitational waves? That they existed?
So it's actually relatively straightforward to take Einstein's field equations and to get a wave equation out of them. And so this is something we do in the GR class in our department. But Einstein, you can see the couplings in front, and you know that they're very weak. And so Einstein thought they would never be detected. I think there's some writing to that effect. Okay, well, thank you very much.